Shooters, reloaders, and conversationalists, welcome to PounderLabs. Today we introduce PounderCap, a new performance metric for precision pistol. In our study of applying analytics to the shooting sports, we think NRA Precision Pistol has a lot to offer. It has a long, rich history of shooting performance, and the platform has both high accuracy and precision requirements. To effectively study this, we felt we needed a new method of evaluating performance. We use a methodology like this, starting with ideas, building models, doing measurement, analyzing and testing data, and what we learn, and loop back through this. So what we're going to offer today, we've done that, and we've done some validation using the Smith Wesson Model 41 with select ELEY 22 long rifle ammo. There's some background information you might be interested in, either on our PounderLabs YouTube channel or also through our PounderLabs website. You might be interested in videos on PounderZ, which covers experimental design, statistical measure, and circular air probable. PounderDrag goes into the elaborate our Doppler chronograph and the calculation of coefficients of drag and ballistic coefficients. To study a system, we need to build a model. Most shooters would agree that shooting performance is tied to the shooter, firearm, ammunition, sighting, and how you make your measurements. Our proposal is to use variance. It's a measure of dispersion as a proxy measurement. So we can go through each of the different elements of this model and look at the associated variances. A model such as this is pretty complicated, so we try to look for simplifications. In this case, we're saying that the variances associated with measurement are much, much smaller than the other elements of the model. We're going to use the on-target software, which can measure down into the thousands. The lab radar has high precision in it, and then the weather flow weather meters used to adjust atmospherics and improve the accuracy and precisions of these other measurements. Sighting is extremely important. Sight picture, sight alignment, and zeroing are all very important, but as you see, they won't be needed in what we're studying today. An important step is to take the variances associated with the shooter out of the equation. And to do that, we're going to use the ransom master pistol rest, and then we're going to use the same handgun for the whole project. So now we have a manageable measurement problem. We're saying the dispersion we're going to see for hits on targets is primarily attributed to the dispersion from the ammo. On these models, you need to allow an error term. First of all, when you're making these kind of simplifications, you do introduce some error. But there's a couple of other things we call confounding factors. An example would be things like for high performance rifle, you're going to have throat erosion, or under sustained fire, you're going to have barrel heating. So although these things aren't measured, they can affect both our parameters of the model and can have an effect on the result. The other thing are constants that aren't constants. So through a shooting session, we'll make atmospheric pressure measurements, and over that period of time, we try to treat that as a constant, even though there might be some changes over the time of the test. You just simply have to be sensitive that those kind of things can occur and affect your outcome. Here's our key test equipment. The lab radar Doppler chronograph and weather flow weather meter won't be discussed any further. You can turn to the PounderDrag video mentioned on the previous slide to learn a lot more about that. This is the ransom master pistol rest. This has been the gold standard for testing handguns and ammo for many decades. Anytime you see in magazines test results given as ransom rest, this is what they're talking about. This particular model is called the combination model, where the windage base is combined with the rest as a single unit. In this case, we have mounted a Smith Wesson Model 52. The football knobs and the baseball knobs are here for adjusting windage. But you'll notice here there's usually what's called star knobs for adjusting the pressure on the platen that holds the pistol in place. With the guidance of ransom rest, we replace the star nuts with these bolts, so now we can use a torque wrench to get very precise measurements of the pressure on the platen that holds the pistol in place. To get an idea, the amount of pressure on this can be easily overdone, and the torque on these is on the order of the same kind of inch-pounds that you have for seating scope rings. The inserts here are an elastomer material that's designed to simulate the hand. So the thing that the ransom rest really does is to simulate as best possible, to an amazing degree actually, exactly the kind of shooting experience that a user would have. So when you look at the results that you get, these things are very equatable to what the shooter can expect when they're shooting on the range. The ransom rest, seldom you see it in this much detail. It's ubiquitous. You know that there's several copies of this in Mythbusters. It's used extensively by the military, police, forensic labs, and of course little research labs like PounderLabs. But we wanted to focus in on it because this is a critical piece of equipment for the success of our testing. Here's a short pan shot of our range setup. You'll find the field notebook always, ammo laid out per our design, spotting scope, the tablet with Bluetooth so we can talk to the lab radar, and the weather meter. You'll see the ransom master pistol rest, lab radar on a bench stand, and the weather meter on a little tripod. Here we go. Here are the test targets for our session. The template for these targets is discussed in depth in the PounderSim video mentioned on a previous slide, so we won't be going through the detail of that here. All of these are shot over a 30-minute period at 25 yards, and they're 10-shot groups. You can see the grouping here across the line with the different ammo. This is done with the ELEY standard, which you can get from the civilian marksmanship program. Here's a relatively new offering called Bullseye Pistol X, which is designed for precision pistol, and this is ELEY Match. You'll notice this group is fairly open in the windage direction. So that's if we saw that originally, since ELEY Match is good ammo, we would tend to rerun that and double check. But this isn't an exhaustive evaluation of these different offerings. This is in here for an illustration, and that extra width and that dispersion we'll use as an example shortly. Here's our table of test results. The different ammo, all shot at 25 yards. Here's the extreme spread. Here's the muzzle velocities, both in feet per second, as well as Mach number. And as we suspect, these are all pretty close. Standard deviation of velocity, 10-shot groups, all shot with the Smith Wesson 41. This is the circular air probable. This is discussed in the PounderSim video in great depth, but just as a reminder, this is a radius of a circle which covers 50% of the shot group. So you can see right here that the ELEY Bullseye on this session was the best. The lower numbers are better. And then here's the ELEY standard, and then here's the match. So we're going to be using this in a lot more detail in a minute as we take this analysis deeper. We're going to borrow a technique from statistical process control called process capability, which is simply a measurable property of a process to a specification. And this is used in manufacturing to set specification limits. This grew out of the Six Sigma program driven by Motorola back in the early 80s, and your humble narrator had the opportunity to participate in some of that development. The capability index is defined with an upper spec limit, lower spec limit, and a population mean and standard deviation. And here's the expression. Simply the upper spec limit minus the lower spec limit divided by 6 times the population standard deviation. As we know, working with populations are difficult, so we accept what's the sampling assumption. So then we're going to use the sample mean, x bar, and the sample standard deviation. So here's the same expression now, recognizing that these are estimates. This is where the 6 comes from. Let's look at this diagram. If we have a mean of 0 and a standard deviation of 1, that gives a capability index equal to 1. Think of it this way. So here's 1, 2, 3 standard deviations. Same thing on the other side. So when you set the mean to 0 here, the 3 runs on both sides. So for the normal distribution to be perfectly centered in there, the value is 6 standard deviations. Now you'll notice in recommendations they make for capability index in manufacturing is to actually get an index of more like 1.3, which is represented here by the orange line. So now the mean is still 0, standard deviation is 0.75. So you see you have a little more room to work with on each side of the specification, and you'll see where that comes in as being very important here in a minute. Now let's see how the capability index can be applied to our needs in shooting. We have a two-dimensional problem. So the way we deal with this is we set the X bar and Y bar to the center of the target. This is the center of impact. When you're actually shooting, if you're not going in the middle of the target, that's an aiming problem. So we don't have to worry about that here. If we look at the expression, the upper spec limit minus the lower spec limit, that's nothing more than the diameter of either the X or the 10 ring. So for the B8 target, the 10 ring is about 3.4 inches in diameter, and for the X ring, it's roughly 1.7. Now the magic comes in using the CEP for the best estimate of the sample standard deviation. The algorithm for calculating CEP is non-trivial, but it's fairly straightforward and comes out of the analysis done with the on-target software. What's very nice about this, in addition to taking a two-dimensional problem and getting it down to one value of sample standard deviation, it allows for when groups aren't around, and that's a very convenient thing. So now we're going to call this PCAP, P capability, and we simply have the new expression here. Bull diameter over 6 times the CEP, and this is the constant that turns the CEP into the standard deviation. So we're able to take a two-dimensional problem and treat it as one-dimensional. You can see the visualization here. You can actually see that both in the X and Y direction, we can have both an upper and lower spec limit, which are the diameter of the bulls. A couple of things to keep in mind. Capability analysis in industry can be much more complex, but we really don't need to get into that here. We're kind of subscribing to the notion that Phil Crosby, who was a big champion of statistical control, kind of using the goalpost model. As long as our shots are falling within these limits here, the diameter of the rings on the target, that's really what was going to be most important to us. So how would we evaluate and take and validate what we're seeing here? We now revisit our session result table and update with PCAP values. We're calling out the target, the B8. Here's our PCAP X for the X ring and PCAP 10 for the 10 ring. And just like we saw with the CEP, where smaller is better, for PCAP values, larger is better. If we set a value of 1, we can go through our calculation and come up with what we can call a critical value for CEP. And the meaning for that is you'd expect to miss about 1/4 of a shot out of a 100-round session. Roughly meaning 1 round out of a brick of 500. So for the X ring, the critical value is 0.3326, and for the X-ring, it's 0.653. But let's look what this means. For this ammo right here, where we're getting a PCAP close to 1, there's the associated CEP, compare that to what we have here. So we're starting to come up on the ability to really hold all those rounds within the X-ring, but we still have plenty of room, plenty of safety margin for the X-ring. Let's look at visualization of this. These two plots are the normal distribution functions based on the PCAP of our test ammo. You'll see as the PCAP increases, you get more and more margin from the edge of the target. This applies for both the X-ring and the X-ring. The one thing you'll notice is that when you're down in the X-ring, because the diameter of the bull is smaller, you got to be careful as you're getting closer and closer to the edge. But you can see within the X-ring, all of this ammo plays very nicely. So we like to look at this space here on how much slide you have between here as a matter of forgiveness. So you have less forgiveness here before you slip out of the X-ring, but you have a lot more forgiveness here before you slip out of the X-ring. So how would we study this more deeply and validate some of what we see? There appears to be some work done on Monte Carlo technique. It's before World War II. But Stanislaw Ohms is credited with the proposal in the late 1940s. John von Neumann recognized the potential of the technique immediately and did the first computer software of it. Nick Metropolis was also part of this effort and is credited by the early 50s of making Monte Carlo methods very popular. Some of the Monte Carlo techniques can be very complicated, but let's take a look at a simple sample. Say you want to find the area of an irregular shaped pond on a rectangular piece of property. So we want to first calculate the area of the rectangle, length times width, will give the area in square foot. The next thing we want to do is start pitching stones. We want to run around the outside of the property, pitching, tossing and throwing big stones and little stones. And all we want to do is keep track of the number of stones we throw. And every time we hit the water, we get a plunk versus hitting the ground, we get a thud. After a while, you can take the number of plunks divided by the number of stones, and that gives you a fraction. So you take that fraction and multiply it times the rectangular area, and that'll give you the area of the pond. But you can see immediately that this requires a lot of stones, and this is where the computer comes in handy. PounderSim is our Monte Carlo simulation system that we put together for the shooting sports. We use it in a lot of different ways, but here we're going to focus on PCAP and how we can use this technique to learn more about it. This really gets down into simulating population standard deviation versus sample standard deviation. Each one of these is a pass through the simulation where there are 10 shot groups and the standard deviation is corrected for sample size, which is the Bessel correction. This is normally done and is what happens when we get the data coming out of the on-target software. We're using the statistics that came from the ELEY batch ammo. Here's the standard deviation in X and the standard deviation in Y, and you'll see it's kind of egg-shaped. And here's the associated PCAP for the X-ring and the PCAP for the X-ring. So you'll notice on each of these 10 round groups, we're hitting the X-ring pretty consistently. This guy right here is a little bit out, but you'll see over and over again that we're fitting comfortably within the X-ring for each of these 10 shot groups. But now what we can do is we can ramp this up, and now we're going to take 90 shot groups. Think of it as running the whole rimfire course of fire all at 25 yards. Now we can start to get a pretty good estimation of population standard deviation. And of course, this isn't corrected for the sample size. And there's also another correction that Grubb identifies in his publication. But once you get above 20 samples, there's not a correction factor there either. So we're getting a pretty good estimation of population standard deviation. So each of these are passes through with these statistics. And notice now that as you start to up that population, you'll start to distinctly see rounds coming out of the X-ring. We're still in the 10 ring all the way across, but we're starting to get more out of the X-ring. And you'll notice that it happens in the horizontal on the windage side, because this particular distribution for this ammo is egg-shaped. So we're able to see just how powerful the PCAP is for not only helping us understand evaluation down with these small samples that we normally use for target shooting, but we can also look at large simulations and understand even more deeply what some of the long-term limitations and insights are. We offer PounderCap as an improved evaluation for precision pistol. It's a single, dimensionless number that completely describes performance. It's simple to determine, and most importantly, based on hits on targets. Other information, velocity, standard deviation of velocity, all these things are important, but at the end of the day, how those rounds print the card is really what matters. Here's another example. We've shown the benefit of applying analytics based on shooter knowledge. We're not inventing anything here. We're using analytics to move forward our understanding, time to solutions, new insights using simple statistical methods. We'd like to extend a special thank you to Mike Ransom at Ransom International for his guidance and valuable counsel. We'd like to leave you with food for thought for the NRA Precision Pistol. The high score is 2680-159. This was shot in the summer of 1974 by Herschel Anderson. So the idea we want to leave you with is to ponder, might the firearm and ammo dispersions limit ever seeing a perfect 2700? This completes our presentation, and as you're thinking about subscribing, please look over these important notes and disclaimers. They're here for your protection and ours. Thanks for watching. See you soon.